From the moment humans first looked up at the night sky, one question has echoed through every civilization, every philosophy, every religion, and now every branch of modern science. What is reality? Are we truly standing inside a solid, objective universe? Or are we merely participants inside something far more complex, far more hidden, and far more unsettling? For thousands of years, this question lived in myths and metaphors. Ancient cultures imagined the world as a dream of the gods, a shadow cast on a cosmic wall, or a fragile illusion sustained by divine will. Plato spoke of prisoners trapped in a cave, mistaking shadows for truth. Eastern philosophies describe reality as Maya, an illusion woven over a deeper truth. These ideas were poetic, symbolic, and philosophical. But today, for the first time in history, the same question is being asked using mathematics, physics, and computer science. This is where simulation theory begins. Simulation theory proposes a radical but logically structured idea that the universe we experience may not be base reality at all. Instead, it could be an artificial construct, a computational environment created and maintained by an intelligence far beyond our own. In simple terms, reality itself may be running on something like code. At first glance, this sounds like science fiction, the plot of movies and novels where characters discover they are living inside a digital world. But simulation theory did not emerge from Hollywood. It emerged from philosophy departments, physics labs, and discussions about the future of technology. It arose not from imagination alone, but from a growing discomfort with how strange reality itself has become under close scientific inspection. The modern formulation of simulation theory is most strongly associated with philosopher Nick Bostrom. In 2003, he published a paper that did not claim outright that we are living in a simulation, but instead presented a logical trilemma. According to Bostrom, at least one of the following statements must be true. Either almost all intelligent civilizations destroy themselves before reaching a level of advanced technology, or advanced civilizations reach that level but choose not to run simulations of their ancestors. Or, if neither of those is true, then the overwhelming majority of conscious beings are living inside simulations, making it statistically likely that we are among them. This argument did not rely on speculation about aliens or gods. It relied on probability. If it is possible to simulate entire worlds with conscious minds, and if such simulations are cheap compared to the resources of an advanced civilization, then simulated realities would vastly outnumber original ones. In that case, being in the base reality would be the exception, not the rule. What makes this idea disturbing is not just its logic, but how well it seems to align with certain features of the universe we observe. Reality behaves less like a smooth, continuous fabric and more like a system with limits. There are maximum speeds, minimum sizes, discrete units of energy, and probabilistic outcomes. Time itself behaves strangely, slowing down and speeding up depending on motion and gravity. Space can bend. Particles can exist in multiple states at once. The deeper physicists look, the less intuitive reality becomes. And this raises an uncomfortable possibility. What if these strange behaviors are not flaws in our understanding, but clues about the nature of the system we are inside? In every computer simulation, there are constraints, processing limits, resolution limits, rules that must be obeyed to keep the system stable. When a game world becomes too complex, developers simplify what is not being observed. They render details only when needed. They impose speed limits, boundaries, and shortcuts to save resources. When physicists describe a universe, they often use language that sounds eerily similar. The universe appears to run on mathematical rules that are astonishingly precise. Equations written on chalkboards accurately predict the behavior of galaxies, particles, and forces across unimaginable distances and times. This raises a profound question. Why should reality be so perfectly mathematical? Why should the universe not only obey mathematics, but appear to be built from it? Some physicists have gone so far as to suggest that the universe is mathematics, not merely described by it. But simulation theory offers another interpretation. Mathematics may not just describe reality. It may be the language in which reality is written. This does not mean that simulation theory is proven. Far from it. But it does mean that the idea cannot be dismissed as mere fantasy. It sits at the uncomfortable intersection of what we know and what we do not yet understand. And perhaps that is why it refuses to go away. As our technology advances, we ourselves are beginning to create primitive simulations. Virtual worlds, artificial intelligence, digital environments populated by agents that follow rules and exhibit behaviors. These systems are crude compared to the universe, but they're improving rapidly. If this trend continues for centuries or millennia, it is not unreasonable to imagine simulations that feel indistinguishable from reality to those inside them. And that realization changes the question entirely. We are no longer asking, could gods have created the universe? We are asking, could engineers have created it? And if they could, then the most unsettling question of all emerges. Not how the universe works, not when it began, but whether it is real in the way we think it is. As science pushed deeper into the structure of reality, something unexpected happened. Instead of uncovering a smooth, elegant continuum beneath the surface of the universe, physicists began to find boundaries, limits, and strange discontinuities. Reality, it seemed, was not infinitely divisible. It had a smallest scale, a maximum speed, and rules that behaved less like natural intuition and more like engineered constraints. These discoveries did not prove the universe was a simulation, but they made the idea increasingly difficult to ignore. One of the first clues comes from the way space and time themselves are structured. At everyday scales, space appears continuous. You can always move halfway between 2 points, then halfway again, and again without limit. But when physicists examine the universe at the smallest possible scales, this smooth picture collapses. Below a certain threshold known as the Planck length and Planck time, the very concepts of distance and duration lose their meaning. Space and time appear quantized, as if reality has a fundamental resolution, much like pixels on a screen or frames in a video. In digital systems, resolution is not optional. Every simulated environment must choose a smallest unit of space and time to remain computationally manageable. Infinite precision is impossible. The fact that our universe seems to enforce such limits raises a troubling question. Why would a truly fundamental reality require a minimum resolution at all? Then there's the speed of light. No matter how powerful a rocket engine becomes, no object with mass can exceed this cosmic speed limit. Information, energy, and causality are all bound by it. From a computational perspective, this resembles a bandwidth cap or processing limit. In a simulation, data cannot be updated faster than the system allows. If information propagated infinitely fast, the system would collapse under its own complexity. The speed of light may not merely be a physical constant, but a structural necessity. Energy, too, behaves in discrete packets. Quantum mechanics revealed that energy is not smooth and continuous, but comes in indivisible units called quanta. Light behaves as both a wave and a particle. Electrons jump between energy levels without occupying the space. In between, these sudden transitions are not intuitive in a classical sense, but they are perfectly natural in digital systems, where values change in steps rather than flows. Perhaps the most unsettling discovery comes from quantum superposition. At the quantum level, particles do not have definite properties until they are measured. An electron can exist in multiple positions at once. A particle can travel multiple paths simultaneously. Only when an observation occurs does reality settle on a single outcome. This phenomenon has puzzled scientists for decades, giving rise to multiple interpretations, none of which are fully satisfying. From the perspective of simulation theory, this behavior has a disturbing resemblance to optimization techniques in computing. In a complex simulation, not every possibility needs to be calculated in full detail at all times. Instead, Outcomes can remain probabilistic until a specific interaction forces the system to resolve them. In other words, reality may not be fully rendered until it is observed. This idea is sometimes described as reality being observer-dependent, not because human consciousness is magical, but because observation represents an interaction that demands a definite outcome. Just as a video game does not render distant environments until the player approaches them, the universe may conserve computational resources by delaying full resolution until necessary. Then there is the strange problem of fine-tuning. The fundamental constants of the universe appear to be set with astonishing precision. If the strength of gravity were slightly stronger or weaker, stars would not form. If the charge of the electron were altered by a tiny fraction, atoms would be unstable. If the expansion rate of the universe were different by a minute amount, matter would never clump into galaxies. These constants appear to sit on a razor's edge. The universe is not just capable of supporting complexity, it is optimized for it. This has led to several competing explanations. Some invoke a multiverse, where countless universes exist with different constants, and we simply inhabit one of the rare life-friendly versions. Others invoke a designer or creator. Simulation theory offers a third option. These values may not be fundamental truths at all, but parameters chosen to produce a stable and interesting environment. In any simulation, variables must be tuned carefully. Too much chaos and the system becomes meaningless. Too much order and nothing interesting happens. The universe appears to exist in a narrow window where complexity, structure, and life are possible. This balance looks less like an accident and more like a configuration. Another digital parallel appears in the way information behaves at the deepest levels of physics. Modern theories increasingly suggest that information, not matter or energy, may be the most fundamental component of reality. Black holes, for example, are now understood in terms of information storage and entropy. The laws of physics appear to conserve information, even when matter is destroyed. If the universe is fundamentally about information, then the idea of it being processed becomes unavoidable. Information is not something that exists without a medium. It must be stored, transmitted, and transformed. These are the defining operations of computation. Yet despite these eerie similarities, it is important to recognize what simulation theory does not claim. It does not say that glitches in reality prove we are in a computer. It does not say that every unexplained phenomenon is a bug in the system. It does not claim that someone is watching us for entertainment. These are cultural additions, not scientific necessities. The theory simply asks whether the structure of reality is more consistent with an objective, self-existing universe, or with a constructed environment governed by computational rules. At this stage, the evidence remains circumstantial. No experiment has conclusively revealed the universe to be a simulation. Every strange feature of physics can still be explained, at least in principle, by deeper natural laws. But the fact that digital metaphors fit so naturally is what keeps the conversation alive. The deeper scientists dig, the more reality resembles something processed rather than something simply existing. And this leads to a far more uncomfortable realization. If the universe can be interpreted as a simulation, then it may not have been created for us at all. If the universe were merely a physical simulation, the idea would already be unsettling. But the theory becomes truly disturbing when consciousness enters the picture. Rocks, stars, and particles being simulated is one thing. Minds experiencing reality from the inside is something far more profound. The central question of simulation theory is not really about physics at all. It is about whether conscious experience itself can arise inside an artificial system. Human consciousness is the most intimate fact of our existence. You can doubt the external world, doubt history, doubt even your own memories, but you cannot doubt that you are experiencing something right now. Thoughts appear. Sensations arise. Emotions move through awareness. This inner world feels undeniable, immediate, and deeply real. If we are in a simulation, then this inner experience is either being generated by the system or it exists in a way we do not yet understand. There are two broad possibilities. The first is that consciousness is an emergent property of information processing. In this view, the brain is a biological machine. Neurons fire, signals propagate, and consciousness emerges from the complex patterns of activity. If this is true, then in principle, the same patterns could be implemented in another medium. Silicon instead of biology, code instead of cells. A simulated brain running the same processes would produce the same conscious experience. This idea is deeply unsettling because it implies that subjective experience is not tied to any particular substance. What matters is not what the system is made of, but what it does. If the functional structure is preserved, the mind exists. Under this view, simulated beings would not be philosophical zombies or empty puppets. They would feel pain, love, fear, and hope exactly as we do. The second possibility is that consciousness is not reducible to computation. It may involve properties of reality that are not captured by information processing alone. Some theories suggest that consciousness is fundamental, like space and time. Others propose that it arises from unknown physical processes that cannot be simulated. If this is the case, then a simulated universe might contain perfect imitations of behavior without genuine inner experience. The problem is that we have no way to distinguish between these possibilities from the inside. If you were a conscious mind inside a simulation, your experiences would feel just as real as they do now. There would be no internal signal that says, this is simulated. Reality would simply be what you experience. This leads to a deeply unsettling conclusion. Even if simulation theory were true, it might be impossible for us to ever know it for certain. The problem becomes even more complex when we consider identity. What makes you? Is it your body, your brain, your memories, or the pattern of information that defines your personality? If your mind were copied perfectly into a simulated environment, would that copy be you, or merely a duplicate? If the simulation were paused, resumed, or run faster than real time, would your sense of self change? These questions are no longer hypothetical. Modern neuroscience already treats the brain as an information processing system. Memories can be altered. Personalities can change due to injury or disease. Conscious experience appears to be fragile, dependent on physical processes. Simulation theory simply extends this logic to its extreme conclusion. Another unsettling implication is the possibility of nested realities. If our universe is a simulation, then it may itself contain simulations. Those simulations could, in turn, contain others. This creates a hierarchy of realities, each one believing itself to be fundamental. In such a structure, base reality becomes increasingly rare, buried beneath layers of artificial worlds. This raises an uncomfortable question. If we are not in base reality, does that make our universe less real? From the perspective of experience, the answer appears to be no. Pain still hurts. Joy still matters. Meaning still exists. Reality, in the only sense that matters to a conscious being, is defined by experience, not by origin. A simulated sunrise would still be beautiful. A simulated loss would still be devastating. But there's another consequence that is harder to ignore. If consciousness can exist inside simulations, then creating them becomes a moral act. A simulated world populated by conscious minds is not a toy. It is a universe full of beings who can suffer. This forces us to confront a mirror image of the problem. If we ourselves are simulated, then whoever created our universe bears responsibility for everything that happens inside it. Natural disasters, disease, violence, and extinction events would not simply be accidents of physics. They would be features of the system, either allowed or engineered. Some find this idea terrifying. Others find it strangely familiar. Throughout history, humans have grappled with the problem of evil. Why does suffering exist in a universe created by a higher power? Simulation theory reframes this ancient question in technological terms. The creator is no longer a god in the traditional sense, but a programmer, an engineer, or an intelligence running experiments for purposes we may never understand. But there is a crucial difference. Unlike religious explanations, simulation theory does not promise meaning, justice, or salvation. It offers no guarantee that the creators care. They may be curious observers, historians reconstructing the past, or entities running simulations for reasons completely unrelated to us. This realization forces us to confront a final, deeply personal question. If your life is part of a simulation, does it still matter? From a rational perspective, the answer is yes. Meaning does not come from the universe being fundamental. It comes from relationships, choices, values, and experiences. A story does not lose its emotional power because it is written in ink rather than carved into stone. In fact, the possibility that reality is a simulation may make meaning more fragile and therefore more precious. As compelling as simulation theory may sound, a serious problem stands in its way. Science is not built on how intriguing an idea feels, but on whether it can be tested, challenged, and potentially proven wrong. This is where simulation theory begins to face its strongest resistance. Many physicists and philosophers argue that the theory may sit forever beyond the reach of empirical science, trapped in a space where logic can explore but experiments cannot follow. The core issue is falsifiability. For a claim to be scientific, there must be some possible observation that could show it to be false. Gravity can be tested. Relativity can be tested. Quantum mechanics can be tested. But how would one test whether the universe itself is a simulation? Any observation we make is, by definition, part of the system we're trying to test. We cannot step outside the universe to inspect the machinery running it. Even if we discovered strange irregularities in physical laws, they could always be explained as deeper natural principles rather than evidence of a simulated substrate. A glitch could be a new particle. A boundary could be a new symmetry. Every anomaly can be absorbed into physics without invoking a simulation. This makes the theory dangerously close to being unfalsifiable. Some have suggested searching for pixelation in space, preferred directions in the universe, or limits in information density that resemble computational constraints. Others propose looking for errors in mathematical consistency or unexpected breakdowns in physical laws. But none of these would definitively prove a simulation. At best, they would hint at unfamiliar structure. Another proposed test involves the search for computational limits embedded in the universe. If the universe is a simulation, then it must run on finite resources. There may be a maximum amount of information that can exist in a given region of space. Interestingly, physics already suggests such limits. The Bekenstein bound and the holographic principle imply that information scales with surface area rather than volume. Some see this as a clue. Others see it as a coincidence explained by quantum gravity. Critics argue that simulation theory risks becoming a modern version of an old philosophical trap. In the past, people explained gaps in knowledge by invoking gods. When science advanced, those explanations faded. There's a concern that simulation talk may be filling a similar role, offering an answer where none is yet available. Another major objection is computational feasibility. Simulating an entire universe, down to every quantum interaction, would require astronomical resources. Even a civilization harnessing the energy of stars would struggle to run such a simulation at full resolution. In response, proponents argue that not everything needs to be simulated in full detail at all times. Only what is observed needs high resolution. The rest can remain approximate. This response, however, introduces new problems. Who or what decides what is being observed? Does every conscious being demand full resolution around them? What happens when many observers exist simultaneously? The complexity rapidly explodes. What began as a solution becomes another mystery. There is also the problem of infinite regress. If our universe is a simulation, then what about the universe running it? Is that universe also a simulation? And if so, what about the one above it? This chain could extend infinitely, raising the question of whether base reality exists at all. Some philosophers accept this possibility. Others see it as a reason to reject the theory entirely. Despite these objections, simulation theory persists not because it solves every problem, but because it connects so many unanswered questions into a single framework. It provides a language that links physics, information theory, artificial intelligence, and philosophy of mind. It does not replace existing science. It sits on top of it, asking a different kind of question. Importantly, simulation theory does not predict specific outcomes in the way traditional theories do. It reframes interpretation rather than measurement. This makes it powerful, but also dangerous. A theory that explains everything risks explaining nothing. Yet history shows that ideas once considered metaphysical sometimes migrate into science. The atom was once philosophical speculation. So is the curvature of space. The question is whether simulation theory will eventually follow the same path or remain permanently philosophical. There is also a psychological dimension to the resistance. Humans are uncomfortable with the idea that reality is not what it seems. The Copernican revolution removed Earth from the center of the universe. Darwin removed humans from special creation. Simulation theory threatens to remove us from base reality itself. Each step has been met with denial, not because the ideas were wrong, but because they were destabilizing. Still, skepticism is necessary. Without evidence, belief becomes faith. Simulation theory must remain a hypothesis, not a conclusion. To accept it as truth without proof would undermine the very scientific principles that led to its creation. And yet, even if it remains unprovable, the theory continues to exert a strange pull on the human imagination. Because the final question is not whether we can prove the universe is a simulation. It is whether we can live with the possibility that it is. If simulation theory is true, or even if it is only possibly true, then its greatest impact is not scientific but existential. It does not merely challenge how the universe works. It challenges what it means to live a life within it. Once the idea is taken seriously, it forces a confrontation with questions humans have always asked, but now in a radically modern form. What is meaning? Do our choices matter? Are we free, or are we following lines of code written long before we were born? At first, the idea of living inside a simulation can feel deeply destabilizing. If reality is constructed, then it may seem that everything we value is fragile, provisional, or fake. Love might feel programmed. Suffering might feel engineered. Achievement might feel pointless. But this reaction misunderstands what gives things value in the first place. Meaning does not come from a universe being fundamental. It comes from experience. A piece of music does not lose its beauty because it is stored digitally rather than carved into stone. A story does not lose its power because it exists inside a book rather than in spoken memory. In the same way, a life does not lose its worth because it unfolds inside a simulated environment. What matters is not the substrate, but the experience itself. Freedom is often raised as another casualty of simulation theory. If the universe is governed by code, are we truly free? But this question existed long before simulations. Deterministic physics already suggested that every event follows from prior causes. Randomness in quantum mechanics did not restore meaningful freedom. Free will has always existed in tension with the laws of nature. In a simulated universe, this tension remains unchanged. Whether the laws are written by nature or by programmers, we still experience ourselves as decision makers. We deliberate, choose, regret, and learn. These experiences define freedom at the human level, regardless of what ultimately underlies them. In fact, simulation theory may make moral responsibility more important, not less. If conscious beings can exist inside artificial worlds, then creating such worlds carries enormous ethical weight. A simulation filled with suffering is not a harmless experiment. It is a moral catastrophe. This realization casts a long shadow over any advanced civilization capable of creating simulated universes. It also turns the mirror back on us. As we move closer to building advanced artificial intelligence and increasingly immersive virtual worlds, we are approaching the threshold where our own creations may become conscious. When that happens, the ethical questions raised by simulation theory will no longer be hypothetical. They will be immediate and unavoidable. There is also the question of purpose. If the universe is a simulation, why was it created? The honest answer is that we may never know. The creators might be scientists studying history. They might be artists exploring possibility. They might be entities whose motivations are so alien that our concepts of purpose do not apply. Or the simulation may have no ongoing purpose at all, running simply because it was started. But this uncertainty does not rob us of purpose. It merely shifts where purpose comes from. Instead of being handed down from the structure of the universe, meaning becomes something we create. In a strange way, this aligns with many philosophical traditions that argue meaning is not discovered but made. Another unsettling implication is the possibility of termination. A simulation can be paused, altered, or shut down. This introduces a cosmic fragility unlike anything imagined before. But even this does not fundamentally change the human condition. Civilizations have always faced extinction. Individuals have always faced death. The possibility that reality itself could end simply scales that uncertainty upward. And yet, there's a quiet hope hidden inside simulation theory. If reality can be created, it can also be preserved, copied, or restarted. Concepts like resurrection, afterlife, or continuity of consciousness take on new, albeit speculative, forms. What once belonged to religion now appears, however faintly, on the horizon of technology. Ultimately, simulation theory does not tell us what is true. It tells us what might be possible. It is a lens through which reality can be reinterpreted, not a final answer. Its true power lies not in whether it is correct, but in how it forces us to think. It reminds us that certainty is rare, that humility is necessary, that the universe may be far stranger than our instincts suggest. Whether we live in base reality or inside a simulation, one fact remains unchanged. We are here. We are conscious. We experience wonder, fear, love, and curiosity. We ask questions. We search for understanding. And perhaps that is the deepest truth of all. If this is a simulation, then it is one in which beings emerged who can question the nature of the system itself. And that alone makes it extraordinary. Because in the end, the most important question is not whether the universe is real. It is what we choose to do with the reality we experience. And yet, even within this uncertainty lies an invitation, a challenge to live fully and consciously. If reality itself is constructed, then every moment we experience is a choice to engage with it authentically. Every act of kindness, every spark of creativity, every pursuit of knowledge becomes a statement of existence. Perhaps the true test of being alive is not discovering whether we are in base reality or a simulation, but embracing the reality we perceive, with all its beauty, suffering, and mystery. In this sense, simulation theory transforms from a threat into a guide. It reminds us that meaning is not inherited from the cosmos. It is created by our awareness, shaped by our decisions, and illuminated by the curiosity that drives us to question everything. The universe, whether simulated or fundamental, becomes a canvas, and consciousness, the fragile, radiant consciousness we possess, becomes the brush with which we paint our experience.